March 23, 1945, 9 p.m., Wesel, Germany. General Lieutenant Friedrich Koechlin, commanding the 88th Corps defending the Rhine's west bank, stood in his command bunker listening to reports that made no tactical sense. American forces, specifically Patton's Third Army, had crossed the Rhine at Oppenheim 24 hours earlier using assault boats. That crossing, while unexpected, was comprehensible within conventional military doctrine. What was happening now, 60 miles north at Wesel, violated every principle of river assault Koechlin had studied in 40 years of military service. The British Second Army wasn't using assault boats. They weren't building pontoon bridges under fire. They were crossing the Rhine, the most formidable natural barrier in Western Europe, on a highway that hadn't existed 6 hours earlier. The highway was floating, constructed from modular steel sections bolted together, supported by pontoons manufactured in British factories, and transported across France in convoys that German intelligence had tracked but misidentified as standard supply shipments. The sections, each weighing 30 tons and measuring 40 feet long, had been assembled under cover of darkness by Royal Engineers working at speeds that seemed physically impossible. By dawn on March 24th, British forces had established a bridge capable of supporting 40-ton Churchill tanks, crossing at 15-minute intervals, traversing the Rhine while German artillery attempted to target a structure that German doctrine insisted couldn't exist. The bridge was Bailey, portable, prefabricated, and capable of being assembled by infantry engineers without specialized equipment or heavy machinery. Invented by Donald Coleman Bailey, a civil servant working in the British War Office experimental bridging establishment at Christchurch, his specialty was structural analysis, specifically calculating load distributions in truss systems. In 1940, assigned to develop portable bridge systems for military use, Bailey recognized that existing designs prioritized strength through mass, creating structures too heavy for rapid deployment. He proposed inverting the design philosophy, create modular panels that could be assembled rapidly in multiple configurations, with strength derived from geometric distribution rather than material mass. The prototype, demonstrated in May 1941, consisted of welded steel panels measuring 10 feet by 5 feet, weighing 570 pounds each, joined by pins that required no specialized tools or heavy equipment. Multiple panels could be assembled into spans of varying length and load capacity. The design was mechanically simple, using Warren truss geometry that civil engineers had employed for railroad bridges since the 1840s. Bailey's innovation wasn't the geometry, it was the modularization, creating a system where non-specialist infantry could assemble bridge components under combat conditions using only hand tools. The War Office's response was skeptical. Military bridges required specialized engineering units, heavy equipment for foundation preparation, and substantial time for assembly under controlled conditions. Bailey's design appeared to eliminate all these requirements, which senior engineers interpreted as evidence that the design sacrificed essential structural integrity. The panels were too light, the assembly method was too simple, the claimed load capacities exceeded what simple pin connections could sustain. The entire concept seemed to violate established engineering principles. Testing proved otherwise. A prototype span, assembled by infantry soldiers with minimal training, supported a 40-ton Valentine tank crossing at 15 miles per hour. The structure flexed under load but didn't fail. Engineers examining the assembly were astonished by how load distribution through the Warren truss geometry transferred stresses to the pins, which experienced shear forces within design limits, despite supporting weights that seemed impossible for simple mechanical connections. The mathematics were sound, the structure worked, and production could begin immediately using existing steel supplies and standard fabrication techniques. The British Army ordered mass production in late 1941. By 1942, Bailey bridges were standard equipment for Royal Engineers. By 1943, American forces were using Bailey bridges extensively in North Africa and Italy. By 1944, Bailey bridges were crossing rivers, ravines, and bomb craters across Europe, replacing destroyed infrastructure faster than German forces could demolish it. The toy bridge had become the most important piece of military engineering equipment in the European theater. The design's genius was flexibility. A single Bailey panel could be configured into multiple bridge types depending on the required span and load capacity. Single used one panel wide and one panel high, supporting light vehicles over short spans. Double used two panels wide and two panels high, supporting medium tanks over moderate spans. Triple used three panels wide and three panels high, supporting the heaviest Allied tanks over spans exceeding 200 feet. The same basic component, assembled in different configurations, created structures ranging from light footbridges to heavy vehicle bridges capable of sustaining continuous tank traffic. German forces encountered Bailey bridges throughout 1943 and 1944, but failed to recognize their strategic significance. German intelligence reports described Allied portable bridge sections and noted rapid construction speeds, but analysts attributed this to specialized engineering units and pre-positioned materials. The concept that infantry units could carry bridge components forward and assemble them under fire without heavy equipment seemed impossible. German military doctrine assumed river crossings required extensive preparation, including foundation work, crane operations, and specialized bridging units operating from secured positions. Bailey bridges bypassed all these requirements. The Rhine crossing plan, developed in early 1945, depended entirely on Bailey bridge capabilities. Allied commanders recognized that German forces would defend the Rhine using conventional doctrine, destroy all fixed bridges, fortify the east bank, and force Allied forces to conduct opposed river crossings using assault boats and pontoon bridges under artillery fire. This doctrine had worked successfully for centuries. River crossings were slow, casualties were high, and defenders could concentrate forces at likely crossing points. Allied planners needed to accelerate the crossing timeline before German defenders could establish effective resistance. The solution was pre-positioning massive quantities of Bailey bridge components along the Rhine's west bank, concealing them in supply dumps that German intelligence monitored but misidentified. Thousands of panels, pins, transoms, and pontoons were moved forward in convoys disguised as general supply shipments. Royal Engineers rehearsed assembly procedures repeatedly, reducing construction time through practice until crews could assemble. German forces encountered Bailey bridges throughout 1943 and 1944, but failed to recognize their strategic significance. German intelligence reports described Allied portable bridge sections and noted rapid construction speeds, but analysts attributed this to specialized engineering units and pre-positioned materials. The concept that infantry units could carry bridge components forward and assemble them under fire without heavy equipment seemed impossible. German military doctrine assumed river crossings required extensive preparation, including foundation work, crane operations, and specialized bridging units operating from secured positions. Bailey bridges bypassed all these requirements. The Rhine crossing plan, developed in early 1945, depended entirely on Bailey bridge capabilities. Allied commanders recognized that German forces would defend the Rhine using conventional doctrine, destroy all fixed bridges, fortify the east bank, and force Allied forces to conduct opposed river crossings using assault boats and pontoon bridges under artillery fire. This doctrine had worked successfully for centuries. River crossings were slow, casualties were high, and defenders could concentrate forces at likely crossing points. Allied planners needed to accelerate the crossing timeline before German defenders could establish effective resistance. The solution was pre-positioning massive quantities of Bailey Bridge components along the Rhine's west bank, concealing them in supply dumps that German intelligence monitored but misidentified. Thousands of panels, pins, transoms, and pontoons were moved forward in convoys disguised as general supply shipments. Royal Engineers rehearsed assembly procedures repeatedly, reducing construction time through practice until crews could assemble a triple span in under 6 hours under optimal conditions. The plan assumed combat conditions would double assembly time, meaning a bridge capable of supporting Churchill tanks could be operational within 12 hours of the initial crossing. Operation Plunder, the Rhine crossing at Wesel, launched on the night of March 23, 1945. British and Canadian forces conducted the initial assault, crossing using Buffalo amphibious vehicles and storm boats, establishing a bridgehead on the east bank under heavy German artillery fire. German commanders, expecting this conventional assault, positioned reserves to counterattack the bridgehead while directing artillery to destroy pontoon bridges that would inevitably follow the initial crossing. German doctrine, based on extensive Eastern Front experience, anticipated that Allied forces would require 2 to 3 days to establish pontoon bridges capable of supporting heavy armor. Royal Engineers began assembling Bailey bridges 6 hours after the initial crossing. The first sections were positioned under smoke cover while German artillery searched for pontoon bridge sites. German forward observers, watching for the distinctive silhouettes of pontoon bridges being assembled under fire, failed to identify the Bailey sections being bolted together at assembly points further back from the riverbank. The sections, transported forward on DUKWs and rolled into position on special launching equipment, were connected while German artillery targeted areas where pontoon bridges should be appearing. By 0400 hours on March 24, the first Bailey Bridge was operational, a triple span, 180 feet long, capable of supporting 40-ton vehicles at 15-minute intervals. German artillery, finally identifying the structure, concentrated fire on the bridge approach. Royal Engineers, working under direct fire, suffered casualties but maintained assembly operations. Additional bridges were under construction at alternate sites. German commanders, monitoring the situation, couldn't understand how Allied forces had constructed a heavy bridge in less than 12 hours without the extensive preparation time that conventional bridging required. The tactical impact was immediate. British armor, instead of waiting days for pontoon bridges to be established and reinforced, began crossing within hours of the initial infantry assault. Churchill tanks, Cromwells, and self-propelled artillery crossed the Rhine at Wesel, while German reserves were still moving into position to counterattack what they assumed would be a lightly held bridgehead. By noon on March 24, British forces had established armored formations on the east bank of the Rhine in sufficient strength to defend against German counterattacks. The bridgehead, which German doctrine predicted would take 3 days to establish and reinforce, was fully operational in less than 24 hours. German commanders recognized immediately that something fundamental had changed in river crossing operations. The speed of the Rhine crossing exceeded any previous Allied operation. Intelligence officers examining reports couldn't reconcile the timeline with known Allied capabilities. The conventional assumption that major river crossings required extensive preparation and predictable construction timelines no longer applied. Allied forces could cross water obstacles faster than German forces could concentrate defenders to oppose them. The Bailey Bridge wasn't limited to the Rhine. Throughout March and April 1945, as Allied forces advanced into Germany, Bailey bridges replaced destroyed infrastructure with speeds that astonished German defenders. Every destroyed road bridge, rail bridge, or crossing point was replaced within hours or days rather than weeks. German demolition teams, trained to destroy bridges and assume weeks of delay before Allied forces could bypass the obstruction, Bailey bridges appeared almost immediately after demolition operations completed. The industrial scale was staggering. British and American factories had produced over 200,000 tons of Bailey Bridge components by March 1945, enough material to construct over 100 miles of bridge if assembled end-to-end. The components were distributed across Western Europe in supply dumps positioned at strategic intervals, ensuring engineer units could access materials immediately when needed. The logistical system supporting Bailey Bridge operations represented one of the most sophisticated supply chains of the war, coordinating production, transportation, distribution, and deployment of specialized equipment across an entire theater of operations. German forces had no equivalent system. German military bridges required specialized equipment, extended assembly times, and engineer units with specific training. When German forces destroyed bridges during retreats, they assumed weeks of operational advantage while Allied forces struggled to restore crossings. Bailey bridges eliminated that advantage. The operational tempo of Allied advances accelerated because destroyed infrastructure no longer created significant delays. The Rhine crossing at Remagen 2 weeks before Wesel had demonstrated the strategic value of intact bridges. When American forces captured the Ludendorff Bridge on March 7, 1945, they gained an intact crossing that allowed immediate armor deployment on the east bank. Hitler ordered desperate counterattacks to destroy the bridge, recognizing that an intact Rhine crossing threatened the entire German defensive position. The bridge collapsed on March 17, killing 28 American engineers, but by then, American forces had constructed multiple Bailey bridges nearby, and the bridgehead was secured. The lesson was clear. Rapid river crossings eliminated German defensive advantages. The Rhine, which should have delayed Allied advances for weeks, was crossed at multiple points within days. German forces, retreating toward Berlin, couldn't establish effective defensive lines because Allied forces crossed rivers faster than defensive positions could be organized. The strategic barrier that the Rhine represented existed for approximately 72 hours before becoming tactically irrelevant. Bailey's invention received minimal public recognition during the war. The bridges were utilitarian, unglamorous, and technically uninteresting to journalists covering combat operations. Newspaper reports focused on assault troops crossing under fire, tank battles, and bombing campaigns. Engineering operations, while tactically critical, made poor copy. Bailey himself remained a civil servant, continuing structural analysis work throughout the war, receiving modest official recognition but little public fame. The American military adopted Bailey bridges enthusiastically, designating them panel bridges M2 in American nomenclature and incorporating them into standard engineering equipment. American factories began producing Bailey components under license in 1943, ensuring adequate supply for operations in both European and Pacific theaters. By 1945, Bailey bridges were crossing rivers from the Rhine to the Philippines, enabling operations that conventional bridging equipment couldn't support in available timeframes. The German response was industrial rather than tactical. German engineers studied captured Bailey Bridge components and recognized the design's efficiency. Several proposals circulated for German equivalent systems, but material shortages and production priorities prevented implementation. By 1945, German industry was struggling to maintain production of essential equipment like tanks and aircraft. Specialized bridging systems received minimal resources. German forces continued using conventional military bridges that required extensive time and resources to deploy. The post-war period revealed how thoroughly Bailey bridges had transformed military engineering. Allied forces had constructed over 3,000 Bailey bridges in northwest Europe between June 1944 and May 1945. Combined span length exceeded 100 miles. Many bridges remained in service for years after the war, supporting civilian reconstruction until permanent structures could be built. Bailey bridges constructed in 1945 remained operational into the 1960s, demonstrating that the design's durability far exceeded its intended temporary military application. The civil engineering applications became apparent quickly. Bailey bridges provided emergency infrastructure replacement following disasters, supported construction projects in remote areas, and enabled infrastructure development in locations where conventional bridge construction was impractical or economically unviable. The modular design that military engineers had valued for rapid deployment proved equally valuable for civilian applications requiring temporary or semi-permanent structures. Donald Bailey received a knighthood in 1946 for his contribution to Allied victory. The citation specifically mentioned the Rhine crossings and the role Bailey bridges played in accelerating the final campaigns in Germany. General Eisenhower, in post-war memoirs, identified the Bailey Bridge as one of the three most important technological innovations of the war, alongside radar and the proximity fuse. The assessment was based on operational impact. Bailey bridges enabled operations that would have been impossible or significantly delayed with conventional bridging equipment. The Germans, studying Allied operations post-war, acknowledged that Bailey bridges represented a paradigm shift in military engineering. The speed and flexibility of Bailey bridge operations had negated defensive advantages that German doctrine relied upon. Rivers, which should have provided natural barriers allowing time to reorganize defensive positions, instead became minor obstacles crossed within hours. The operational implications extended beyond tactical engineering to fundamental questions about defensive warfare in the industrial age. Modern military bridges remain modular, portable, and rapidly deployable because Bailey established the design principles in 1940. Contemporary systems use improved materials and construction techniques, but the fundamental concept, prefabricated panels assembled without heavy equipment by personnel with minimal training, derives directly from Bailey's work. The American Medium Girder Bridge, the British General Support Bridge, and various other military bridging systems all employ design philosophies that Bailey pioneered. The Rhine crossing at Wesel demonstrated what Bailey bridges enabled at maximum operational scale. A major river crossing, executed under fire, with heavy armor deployed across a bridge that didn't exist 18 hours earlier. The operation succeeded because Bailey's design allowed rapid assembly at speeds conventional military bridging couldn't match. German defenders, expecting weeks of preparation time, faced armor assaults within hours. The defensive advantage that the Rhine represented disappeared overnight. General Lieutenant Cochling, watching British armor cross the Rhine on March 24, 1945, understood that conventional defensive doctrine had been rendered obsolete. The assumption that major rivers provided weeks of operational advantage while attackers struggled to establish crossings no longer applied. Allied forces had solved the river crossing problem through industrial production and engineering innovation, creating capabilities that defensive planning couldn't anticipate or counter. The Bailey Bridge wasn't a revolutionary technology. The Warren Truss geometry dates to the 19th century. Modular construction wasn't conceptually novel. The innovation was applying known engineering principles to solve a military problem that everyone assumed required complex, specialized solutions. Bailey recognized that simplicity and modularity were strengths, not limitations. The design that senior engineers dismissed as too simple to be effective proved more effective than complex systems, specifically because it was simple. This pattern appeared repeatedly during the war. The best solutions often weren't the most sophisticated technologies, but the most practical implementations of known principles. The T-34 succeeded through mass production. The B-17 succeeded through survivability and numbers. Cullen's hedgerow cutter succeeded through improvisation. Lamar's frequency hopping succeeded through elegant concept implementation. Bailey's bridge succeeded through modular simplicity. The Rhine crossings in March 1945 ended German defensive operations in Western Europe. The river that should have provided weeks of operational advantage became irrelevant within days. German forces retreating toward the Elbe couldn't establish effective defensive lines because Allied forces crossed every river and obstacle faster than defenses could be organized. The Bailey Bridge eliminated the time advantage that natural barriers provided, accelerating Allied advances and compressing the final campaign timeline. The war in Europe ended on May 8, 1945, 46 days after the Wesel crossing. The rapid Allied advance following the Rhine crossings contributed to the collapse of organized German resistance. German forces, unable to establish defensive positions behind natural barriers, fragmented into isolated units that surrendered piecemeal. The Bailey Bridge, by enabling rapid river crossings, helped accelerate the war's conclusion by weeks or possibly months. Donald Bailey died in 1985, having witnessed his invention become standard infrastructure technology worldwide. Thousands of Bailey bridges remained in service decades after the war, supporting civilian traffic in locations where permanent bridges weren't economically justified. The design that military engineers dismissed in 1940 had become ubiquitous, proving its worth through sheer operational utility. The German generals who expected the Rhine to delay Allied advances for weeks learned the lesson every defender eventually learns. Defensive advantages depend on attackers being unable to solve tactical problems faster than defenders can exploit them. When attackers develop capabilities that negate assumed advantages, defensive doctrine becomes obsolete. The Rhine, which German planning assumed would provide a substantial operational advantage, provided approximately 1 day of meaningful delay because Allied forces could construct bridges faster than German doctrine anticipated. The crazy river trick wasn't particularly crazy. It was practical engineering applied with industrial efficiency. Bailey bridges worked because they were simple enough for infantry to assemble, strong enough to support armor, and available in quantities sufficient to cross every river Allied forces encountered. The Germans expected conventional river crossings requiring weeks of preparation. Instead, they faced bridges appearing within hours, constructed by engineers working under fire, using equipment that German intelligence had tracked but misidentified throughout the preceding months. The death ray never worked because physics imposed limits that engineering couldn't overcome. The B-17 worked because mass production and survivability mattered more than technical perfection. The T-34 worked because crude simplicity in overwhelming numbers beat precision engineering in insufficient quantities. The Bailey Bridge worked because modular simplicity enabled rapid deployment at scales conventional bridging couldn't match. And the Rhine, which should have delayed Allied advances for weeks, was crossed in a single night using a toy bridge that senior engineers had dismissed as unsuitable for combat operations. 79 years after Royal Engineers assembled Bailey bridges across the Rhine under German artillery fire, Royal military forces worldwide still use modular bridge systems derived from Bailey's design. The river crossing that German commanders expected would require weeks of siege warfare was accomplished in hours, using equipment that German intelligence had failed to recognize as strategically significant. The floating highway that appeared overnight at Wesel existed because a civil servant had proposed a simple solution to a complex problem, and because Allied industrial capacity had produced that solution at scales sufficient to cross every river in Western Europe. The Germans woke on March 24, 1945, to find British armor on the Rhine's east bank, having crossed a bridge that shouldn't exist, using capabilities German doctrine had never anticipated. The defensive advantage that the Rhine represented vanished overnight. and the war continued with Allied forces advancing unopposed across Germany, crossing rivers and obstacles at speeds that rendered defensive planning meaningless, using simple steel panels bolted together by infantry engineers who had learned that sometimes the best solution to an impossible problem is the obvious one that everyone dismissed as too simple to work. The bridge was Bailey, the river was the Rhine, the crossing took one night, and the German defensive strategy, predicated on rivers providing weeks of operational advantage, collapsed because someone had invented a toy bridge that actually worked.